Hi, I'm Dr. Jim Zoval, a professor of chemistry at Saddleback College. You're about to watch one of my video lectures. If you like this lecture, you can get the entire Allied Health General Organic and Biochemistry course from the website address you see on the screen right now. Be sure to type the underscore between VOD and pages in this address. Enjoy the video. In the next two chapters, chapter 10 and chapter 11, we're going to have a lot of organic chemistry. They're pretty much all organic chemistry. We saw a little bit introduction of organic chemistry up to now, but these chapters will be 100% organic chemistry. And we're going to see a lot of reactions in these chapters. The reason we're looking at these reactions in chapter 10 and chapter 11 is because we're going to see these same types of reactions in all the biochemistry. But now you're going to look at some of the biochemistry in those chapters, and you've probably seen some of it before, maybe in your biology books, but with your new understanding of chemistry, you're going to understand that on a much deeper level. The way we're going to do the organic chemistry chapters is we're going to introduce a family of organic compounds. For example, in this chapter, we're going to look at carboxylic acids, briefly phenols, and amines. And we're going to introduce this family of compounds. We're going to talk about what their structure is, why they're in that particular family. What's their structure, how we name them, what are their properties, and how they react. So we'll do that for different organic families all the way through chapter 10 and chapter 11. I said you're going to see a lot of reactions. And it could be intimidating, go, oh my God, I have to memorize all these reactions, but you don't. On your exam number 3, you get a full piece of paper to write down the chemical reactions, so you don't need to memorize them. What you'll need to do is apply them, and I'm going to show you how you do that. And you guys are going to have plenty of practice to do that. I've got, for chapter 10 and chapter 11, a couple good worksheets at the end of those chapters. For chapter 10, for example, there's a worksheet called Naming the Compounds of chapter 10. And there's also a worksheet called The Reactions of chapter 10 for you guys to practice on. So let's get started. The first family of compounds we're going to look at are carboxylic acids. The general form of a carboxylic acid is this. You have a hydrocarbon connected to a carboxyl group. This is a carboxyl group over here. We've seen this before. We were first introduced to these in an earlier chapter. What we're going to do from now on, instead of having a big box that says hydrocarbon, we want to save some time. So instead of that, we're going to use the symbol R. R represents any hydrocarbon. It could be methyl, it could be ethyl, it could be propyl, it could be a long branched hydrocarbon, just any hydrocarbon. We're going to write R instead of this box right there. Like that. It's hydrocarbon. It would have been nice to have been able to use H, but unfortunately H is already taken. H is hydrogen. This carboxyl group can be written shorthand in condensed structures as COOH, see, COOH. Or you could alternatively write CO2H. When you see this or this, the reader of that is supposed to understand that that and that CO2H mean this in this bonding pattern. The question is, I can't remember what these symbols are. That's the Greek lowercase d delta. And that means you have a highly polar bond here, showing that carbonyl group is highly polar, just like this one and just like this one. And so it's showing that this is a polar molecule over here on this side. On this side, it's nonpolar. So that means partial negative, partial positive. Remember, it's the same as drawing that arrow with the plus on the one end of the arrow, and the arrow points to the negative side. It represents an electric dipole. How do we name carboxylic acids? If you got a pretty good understanding when we named alkanes, alkenes, and alkynes, it'll be an easy transition to name all the other organic families, including carboxylic acids. What we do first is we identify a parent chain. For carboxylic acids, the parent chain is the longest continuous carbon chain that includes the carboxyl group. So the longest chain that has that carbon in it. That's the carboxyl group. The carboxyl group is composed of a carbonyl group, C double bonded to oxygen, and a hydroxyl group, an OH. We call this carbon the carbonyl carbon because that's the carbon that's double bonded to the oxygen in the carbonyl group. When we number the parent chain, the carbonyl carbon is always carbon number 1. So it would be carbon 1, 2, 3, etc. When we have substituents, we list them out in front in alphabetical order, just like we did for alkanes and alkenes and alkynes. For example, here's a carboxylic acid, specific carboxylic acid. When we number the parent chain, that's going to be carbon number 1, the carbonyl carbon. We have to do something to the name to differentiate it from an alkane. If it was just 3 carbons and it was an alkane, we would have said propane. What you do for carboxylic acids is you replace the E in the propane name, the E suffix, with oic acid suffix. For example, 1, 2, 3 carbons, the alkane name would be propane. We replace the E with oic acid and would call this molecule propanoic acid. In this example, there's no substituents. If there were substituents, we'd put their position numbers and list them in front of the parent name. Let's do an example together, then I'll have you guys work on a couple. If I'm going to name this, first thing I'd do is I'd look at that and I say, aha, it's a carboxylic acid. So now I know which carbon is going to be carbon number 1. That carbon is going to be carbon number 1. I choose the parent chain, the longest continuous chain of carbons that include that carbon. So 1, 2, 3, 4. Note, I could have gone 1, 2, 3, 4, and it would have been the same compound, the same name, whichever parent chain I chose. So I'll just choose this as the parent chain. So 1, 2, 3, 4 carbons. The alkane name would be butane. I get rid of the E on the end of butane and I say butanoic acid. I have a substituent. It's on carbon 3. 1, 2, 3. That's a methyl group. So I have 3-methyl-butanoic acid. You guys try a few. I have 3 problems for you in the notes. The first one where I give you the structure and I want you to write the name, then 2 others where I give you the name and I want you to draw the structure. When I ask you just draw the structure, you get to choose whether you want to draw line bond, condensed, skeletal, whichever one you want. If I tell you specifically sometime draw the condensed, then of course you have to draw the condensed. Go ahead and work on those 3.
Do the next 3 problems in your lecture notes. The first one, I give you the formula, you give me the name. The next 2, I give you the names, and you write the formula. Don't try to do that 4th one yet.
Let's think about this one. How many carbons in the parent chain? So that would be hexane if it was the alkane. So the carboxylic acid is hexanoic acid. Now we have 2 substituents, one here and one here. So 3-ethyl, 4-methyl. We put them in alphabetical order, so ethyl goes before methyl. So we have 3-ethyl, 4-methyl hexanoic acid. Check your answers on these. There's the condensed. You might have done the skeletal structures, or you might have done the line bond structures. Any questions? No? We good to go? Sure? Question?
So why is it CH2, CH3? Can you do CH3, CH2?
Let's draw that out. The question was, why did we write CH2, CH3? Why didn't we write CH3, CH2? I think you'll see that would violate the octet rule. I won't draw the parent chain, but that's supposed to represent the parent chain. Let me draw this carbon, say right here. Now, let's see how the binding goes. If we have the next one, if we have this as CH3, it would be C. Here's the other carbon, H3. And H2, right? What's wrong with this? Violates the octet rule here and here. Right? You got 10 electrons around that carbon, right? That's a felony in some states. And you only have 6 here. Other questions?
Yeah, but if you put CH3, CH2, but connect it when the CH2 can...
Oh yeah, that'd be fine. You could do this. Here's the parent chain. And if you did this, right here, you're talking about doing this, right? Yeah, that's fine. Right? Is that what you meant?
No.
Okay. She's honest at least. Good job. Okay. So this is, we could have done this, and I did it in line bond. You could do this, CH2, CH3. That's fine. Or you could do this, CH2, CH3. Or you could put it over here. But the bond to the parent chain has to be to the CH2.
Could the carboxyl group be on the left side as well?
Yeah, very good question. Question was, can the carboxyl group be on the left? Yeah. I'm in the habit of drawing it on the right, and sometimes a lot of books put it on the right. Maybe that's why I'm in the habit of doing it on the right. But let's do it. Let's draw this with the carboxyl group on the left, and let's name it and see if we come up with the same name. So six carbons. 1, 2, 3, 4, 5, 6. We'll put the carboxyl group over here. And let's see, we have a substituent on carbon 4. So this is carbon 1 now because that's the carbonyl carbon. 1, 2, 3, 4. Carbon, carbon. And I'll go and put the hydrogens in. Let me circle the parent chain. Parent chain's there, right? There's carbon 1, there's carbon 4. Here's a substituent here. So 6 carbons. We have hexanoic acid. We have a substituent on carbon 1, 2, 3, 4. It's 4-ethyl hexanoic acid. You know what the difference is? I look at it like that. But if I were to get on the other side of the board, and this was a transparent board, and looked at it from behind that wall on a transparent, it would look like that. So it's just like I have the same name, no matter which way, right? Just same molecule, same connectivity. Good questions. Sometimes carboxylic acids are given common names. They're just historical. That's what they called them. It wasn't till later on in history that the scientists got together, the International Union of Pure and Applied Chemists, IUPAC, got together and said, let's standardize the names so when we publish papers, we're all talking about the same thing. Those are the names that we've been doing, the systemic names. And those are the names that you'll be responsible for on Chem 108 exams. I give you some common names sometimes. You're not responsible for common names on the exam, but just FYI kind of thing. Methanoic acid, when you have 1 carbon, the common name is formic acid. Ethanoic acid, when you have 2 carbons, the common name is acetic acid. White vinegar is a 5% acetic acid solution. I want to introduce a new type of substituent to you on this slide. 3 new substituents. We've only seen alkyl groups as substituents. Ethyl, methyl, propyl, isopropyl. I want to introduce 3 more. I want to introduce hydroxy as a substituent, chloro as a substituent, and bromo as a substituent. If you see the parent chain and there's a hydroxy coming off of it, this is a hydroxy. You see this coming off the parent chain. That's supposed to be the bond to the parent chain. Would call that a hydroxy substituent. And you'd put, let's say it's on carbon 2, you put 2-hydroxy. If you see a chlorine bound to the parent chain, that's chloro. You'd say 4-chloro. And if you see a bromine bound to the parent chain, that's a bromo substituent. So having said that, would you guys draw these 4 molecules? I give you the name, you draw the molecule. For example, this one, 2-hydroxy propanoic acid, you'd just draw propanoic acid, and on carbon 2, you'd put a hydroxy group. If you're watching the video, click pause and work on these 4 problems. Thank you, volunteers, for coming and putting these up.
Click pause and check your answers now.
They look good to me. Hi, I'm Dr. Jim Zoval. If you like this video and you like to get the entire course or just some of the chapters on video, I have the entire course in video lectures at the website you see on the screen right now. They're available on demand. The period of the rental is for a full year, so you'll have this video through the entire course. You could watch it as many times as you want, whenever you want. Happy studies.